So let's do an analysis. So we have to choose, because we're dealing with statics here. We have to choose a system of coordinates, and for convenience, I'm going to choose the CGS coordinates. Okay. So in the CGS coordinates, we can say, okay, what is a centripetal force? So what is the centripetal force on an electron? In a circular orbit. So, okay, I should back up a little bit and say why. So we are assuming circular orbits as a simplifying assumption. Okay. We can take elliptical orbits, but the analysis will be more difficult. So, the circular orbit, you can get a lot of mileage out of it. So, for the sake of argument, let's just do the circular orbits. And the other, so we assume circular orbits. We also assume that the proton mass is the proton does not move. Okay. So if the proton does not move, that then means that the proton mass, or the nucleus, sorry, I should say nucleus, it's only the proton in the case of hydrogen atom has infinite mass. Okay. So if that is the case, then we can ask, what is the centripetal force? So we know that the centripetal acceleration is v squared by a, where a is the radius of the orbit. So the centripetal force is mv squared by a, and that of course has to be supplied by the Coulomb force. And if the atom has an atomic number z, then the Coulomb force is z e squared, where e is the charge of the magnitude of the charge of the electron. So the electron has charge minus e divided by a squared. Okay, so this is our simple force equation. Now the kinetic energy of the electron is going to be half mv squared. Okay, and which, if we use this, can be written as, if we use this guy, we can write that as z e squared by 2a. Now we come to the angular momentum. The angular momentum p phi is simply mva, right? P, this is P, the linear momentum, and this is R, right? So that is basically our angular momentum for circular orbits. Okay? And according to Bohr, this has to be quantized in units of h bar, where n is a natural number. Okay, so now using this, we can find, we see that the allowed speeds of the electron is discrete, so we can label it by n, and it's given by n h bar divided by m times a. Okay, actually, it's better to see it as the allowed values of the radii. Okay, so then what we can do is that we can then solve we can then use v, and we can eliminate v, say, from this equation, and we get the allowed values of an, and the an are given by n squared h bar squared divided by mz e squared. So these are the allowed values of the orbits. So this is basically what gives you the discrete stationary orbits.
Excuse me. What's
Yeah,
Z?
Z is the atomic number.
Oh, I see. Okay.
So the charge of the nucleus. So these are what. So we are describing what is known as the hydrogenic atom. So discrete stationary, states. Okay. So the lowest value,
What was P5?
the angular momentum of the electron in circular orbits. Okay, so angular momentum of the system, because it's really the electron that's moving. So, all right. So for n equals to 1, we get A1, but for some reason it's written as A0. It's h squared divided by m e squared. So n equals to 1 and z equals to 1. So this is the size of the orbit. Size of the orbit of the hydrogen atom of
The
the
lowest orbit.
lowest orbit, I should say size of the orbit of the lowest orbit. Of the hydrogen atom. Okay. So what is the energy? So okay, what is this value? This value turns out to be 0.528 into 10 to the power minus 8 centimeters. Okay, very, very small, or 0.528 angstrom. Okay, so what angstrom is not really used anymore, but in atomic physics, it used to be a very convenient unit. 1 angstrom is 10 to the power minus 8 centimeter. So what is the total energy of the atom? Well, it is sum of the kinetic and the potential energy. And the kinetic energy we have already seen is Z e squared divided by 2a. And the potential energy is, of course, Z e squared by a. And therefore, the total energy is minus Z e squared by 2a, or minus t. So note that the total energy is negative, okay? Is that a surprise?
Is this related to potential?
Mm,
I mean,
yeah,
the surface is 0, and the further you go, you get minus.
Right. So, what does negative total energy tell us? If you, the potential energy, if you define the particles being, separated, so, classically, we define the potential energy of two charges to be 0 when they're infinitely separated, right? And therefore, when they are closer together, because the potential energy is negative, right? If the charges are of opposite charges. What does that say about the system? Can someone tell me what does negative total energy imply about a system? Of course, here we are assuming a particular, a particular value of the potential energy in which the potential energy is zero when the particles are infinitely far away, right? When A is infinity, the potential energy part is zero, right? Otherwise, it's negative. So, but the total energy being negative means that it's a bound system. Okay, bound system. So in bound system, the total energy is negative. So, the hydrogen atom also has unbounded states. So if you give it enough energy, it will become an unbounded state. And that actually is a good way, a segue into the next formula. The next formula is that the total energy, we can now use our value of A in this formula. Then the total energy of the hydrogenic atom is minus Z E squared divided by 2AN. But now if we put in the value of AN here, we get minus M, the mass of the electron, Z squared, the charge of the particle, of the proton, squared, E to the power 4, divided by 2N squared H bar squared, okay? So it's worth writing down, minus M Z squared E to the power 4 divided by 2N squared H squared. Okay. And
So what is a bound system?
a bound system is a system where the particles are not free. They are like, so for example, if you have a positive charge and a negative charge, that's a bound system, right? So they're attracted. So you and the Earth is a bound system. You are not free of the Earth, right? You're in a potential well created by the Earth and you.
What's an example of unbound system?
You in a spaceship far away from the Earth. Or if I go to the hydrogen atom, so this is the energy of the hydrogen atom, see that its energy levels are negative, right? What is the most, negative energy level? That's E, 0, which is for -1. So for hydrogen, Z equals to 1. This is minus M E4 divided by 2H squared, right? So this is the ionization energy of the hydrogen, right? So, the hydrogen atom energy level. So if this is 0, right? This is 0. This is E0. Then the hydrogen energy level are, it's 1 over N squared, right? So the differences between them. And so if you give the hydrogen, suppose the electron is here, and if you give it a photon, which is exactly whose energy is given by the modulus of this, what will happen is that this electron will jump and and become free, okay? And then the proton and the electron would form a free system. Okay. Then the energies of the energy of the would it still be a free system? Yeah, I think so. Yeah, the energies of the proton of the electron would be continuous. It's only so in quantum mechanics. Okay, let me just first, you know, look at the application of this formula. This formula is something, the important part is that this formula is that there is a constant divided by n squared, okay? This is the form of the energy, where RH is a positive constant, and I think it's called the Rydberg constant. And it's so the energy levels of the hydrogen atom or the hydrogenic atom is -1/n². Okay, these are the energy levels of the bound states.